I'm Debbie Liu, the Associate Director of eSig, and I want to welcome everyone to this special webinar. For those of you who aren't familiar with eSig, we are a membership-based nonprofit organization. We provide members with information, resources, and networking opportunities to support clean energy and energy systems integration decisions. And we do this through workshops, tutorials, webinars, blogs, working group and task force activities, and we produce technical resource materials. We also lead one of the pillars of the Global Power System Transformation Consortium, or GPST, and that mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and speed. And more information on that can be found at globalpst.org. Here at eSig, we're all gearing up for our forecasting and markets workshop in Salt Lake City next week. Our workshops and monthly webinars, they're open to everyone. Please feel free to register anytime on our website at www.esig.energy. You can also find us on LinkedIn, YouTube, Facebook, and Twitter. So just a few logistical matters before we get started. All the participant lines are going to be muted for the duration of the webinar. For Q&A, we've moved to the Slido platform. We're asking that you ask your questions at slido.com. So go to slido.com and enter ESIG and then the number 6. So ESIG 6 as the event code. You can see the instructions here at the bottom of the screen. There's also a thumbs up button next to the questions so you can cast a vote to help prioritize questions that are submitted. And we're going to save 10 or 15 minutes for Q&A at the end. We'll wrap it up at the top of the hour. You'll get an email with a link once the video file has been posted. And we'll also plan to provide short responses to unanswered questions after the webinar. So please don't be afraid to ask questions through slido.com. So today we're talking about the Atlantic Offshore Wind Transmission Study. As you all may know, future studies typically rely on us building large amounts of solar, wind, and batteries to decarbonize the grid, because these are relatively inexpensive resources. And you all likely know solar can be sited in many places, but wind growth can be stymied because of siting, permitting challenges, and lack of transmission. And when we think about the eastern seaboard, the densely populated region along that seaboard can make that even more challenging. So offshore wind potentially provides a solution for the eastern seaboard. Transmission, however, can be difficult because there's limited numbers of places where you can land those cables onshore. And on the other hand, offshore wind transmission network options can potentially provide a solution to reinforcing the aging grid. A couple years ago, NREL, the National Renewable Energy Laboratory, launched the Atlantic Offshore Wind Transmission Study to examine how offshore wind and transmission could help the Eastern interconnection. I was lucky to be part of this technical review committee to see this analysis unfold. And today we're really excited to welcome the leaders of this study from NREL to present the results. So first, we're going to have Dr. Greg Brinkman. He led the study. He's an expert in power systems modeling and renewables integration. Much of his work also focuses on transmission in a future low-carbon grid. I've been really lucky to work closely with him in a past life, and he's among the best modelers out there. Then we'll have Dr. Luke Lavin. He's a research engineer in the Grid Planning and Analysis Center, where he develops models, tools, data analyses for valuing the contributions of electricity technologies and uses for future power systems. And then finally, we'll have Dr. Amy Rose. She's a senior researcher and a group manager for the Transmission Group and the Grid Analysis and Planning Center, where she works on planning and operations of low emissions transmission systems. So just a short reminder again, go to slido.com, use the code E66 to ask questions. And now I'd like to turn it over to Dr. Greg Brinkman to get us started.
Thanks, Debbie. Appreciate it. Can you hear me?
Yes.
And see my slides?
I can't see the slides.
Anyone else? It says I'm sharing.
Stop your share and then reshare again.
Okay. Stop. Ryan, any chance you can be backup sharer here? I
Yeah.
can't explain what happened in the last 3 minutes since I was sharing last, but
Go ahead and share.
I can see it.
Okay, I'm
great,
sharing.
thank you.
Yep.
Great, yeah, if you could go back to the title slide. Great, thanks. Yeah, I'm Greg. As Debbie mentioned, I'm Greg Brinkman here today with my colleagues Luke Lavin and Amy Rose on behalf of a larger team from the National Renewable Energy Lab, the Pacific Northwest National Lab, and the U.S. Department of Energy. And as Debbie mentioned, several years ago, the Department of Energy asked that the labs pull together a study to address some of the key questions regarding offshore transmission, and specifically that stakeholders were asking, and specifically questions that were not already being addressed by other studies. So these questions are primarily interregional in nature and challenging for a single region to study. Now, our first step was to bring together a technical review committee to help review the study goals, methods, assumptions, and eventually the conclusions. This group represented a wide range of stakeholders, including folks from system operators, utilities, developers, consultants, etc. There may be a few of those people online today, and the team would like to thank all these people for helping to make the study as relevant as possible. Please do note that the conclusions and assumptions were guided by the advice of our technical review committee, but don't necessarily represent the views of any individual or organization on the committee. The study was released in March, and we have a website with links to the report and an executive summary. So today I'm going to introduce the study and some of the key goals, caveats, and scenarios. Then I'll turn it over to Luke to discuss some of the results of the grid modeling, and then to Amy Rose to discuss the economic modeling and wrap things up. We hope to leave plenty of time for questions too. Next slide, please. So I'll start today by talking about some of the overall goals and objectives of the study, and then we have a few slides discussing the build-outs that we focused on, and then we'll discuss some of the key findings and take-home messages. Our key objective for the study was to determine what some of the potential costs, benefits, and impacts of offshore wind transmission networks could be in a future grid. So the diagram on the right here shows the concept of an offshore transmission network. On the left in that diagram is an example of a radial system, which has no offshore network. Each offshore platform is connected to an onshore point of interconnection, or POI, and there's no connection between the offshore platforms. On the right is an example of a simple offshore transmission network. In addition to the two export cables connecting from the onshore grid to the offshore platforms, there's an interlinking cable connecting those offshore platforms. This interlinking cable could use either high voltage DC or HVDC or AC technology, and it can help contribute to congestion management, curtailment reduction, reliability and resilience, and we wanted to try to quantify some of these impacts. We studied different scenarios and pathways of offshore wind development in the Atlantic through the year 2050, with 85 gigawatts of offshore wind generation capacity in the Atlantic being our 2050 target, and we're studying between Maine and South Carolina. We created our offshore transmission layouts while attempting to respect other uses of the ocean, including conservation, shipping, military, seabed, and other considerations. Next slide, please. This slide shows some of the topologies we analyzed in detail for the study. We'll be using the term topology to describe the layout of the offshore transmission connections and what different types of networks could potentially exist. Now, Luke is going to talk about each of these in a little more detail later, but I wanted to introduce the term and the different ones up front here. We started with the radial topology. This topology assumes direct connections from the offshore platforms to the points of interconnection on the grid with no offshore wind networking and no interlinking cables. And this topology is the basis for all the other topologies. So the export cables, generation locations, and POIs are the same in all the scenarios. Only the offshore network connections are different. So next we have the interregional topology. This topology connects platforms and POIs between different regions in the Atlantic, and it was specifically designed to take advantages of opportunities to connect between regions, possibly with diverse resources and diverse demand patterns wherever possible. The map on the right is a geographic representation of what the interregional topology could look like. And as I mentioned, Luke is going to show some maps for the other topologies in a few minutes. The intra-regional topology connects platforms within regions. This could complement the interregional and possibly come before the interregional topology and interregional solutions are developed. The intra topology is a combination of both the interregional or between region and the intra-regional or within region. All of the interlinking cables in both of these topologies are included in the intra. And we looked at this topology specifically to understand whether the benefits of the two different strategies were additive or whether the development of one could possibly undercut the value of the other. The backbone topology then is a larger and longer version of the interregional build, connecting all the way from Maine through South Carolina. Next slide, please. Thank you. In addition to our key objective, we used a variety of different models to address more specific questions. We performed a bottom-up analysis of offshore substation and cable costs to understand the potential costs of the interlinking and the radial topology. And to understand some of the economic benefits, we simulated a year's operation for all the topologies with the 85 gigawatts of offshore wind generation and an analysis of different sensitivities using Energy Exemplar's Plexos production cost model. And we assessed the resource adequacy, reliability, and some of the resilience impacts using NREL's probabilistic resource adequacy suite model, Siemens PSSE, and PNL's C-Page model. The resource adequacy work was done with 7 years of different meteorological patterns with consistent wind, solar, and demand profiles for all the regions and all the meteorologies. And the wind data is from the NREL Wind Toolkit dataset. Solar data is from the National Solar Radiation Database, and the demand data is based off work from Evolved Energy Research. The resilience work was primarily to demonstrate potential capabilities, and for today's webinar, we'll focus primarily on the results that we were able to quantify economically. And last, we wanted to determine if and how an interregional topology could possibly be developed in stages, achieving some of these benefits without adding near-term hurdles that could be introduced by pre-building transmission. And Amy's going to talk a little bit more about this. And we did this by developing topologies that are consistent with current trajectories where possible and consistent with the technical readiness of potential interlinking topologies and interlinking technologies. Next slide, please. So this slide shows some of the key caveats and what the study is and what it isn't. It is intended to be a big picture analysis of the operation, the economics, and some of the reliability implications of different offshore networking strategies as we've discussed. It's not an interconnection study or a comprehensive reliability analysis. We're focused on long-term futures through the year 2050, focused primarily on the offshore wind and not intending to fully analyze the future grid, especially potential major demand amplification, which would require separate and detailed study. As I mentioned, we have a focus area from Maine through South Carolina. And while the Canadian grid is relevant to the questions being asked, we included Canada in our modeling, we didn't consider any offshore interlinking with Canada. And regarding the cable routing analysis that I'll show in just a couple slides, it's a general routing analysis, and it doesn't have the same level of detail or comprehensiveness needed for an actual siting or a permitting study. And this study is not a suggestion or prescription for specific interlinks or points of interconnection. It's intended as an illustrative comparison between the different offshore transmission networking philosophies. Next slide, please. So next I'll talk about some of the scenario, and then Luke will talk about some of the topology design work that we used to set up the study for more detailed analysis. This work was used to create a set of future grid states that we could compare using more detailed transmission models, focused primarily on 2050 and the full development of the different topologies. Next slide, please. So offshore wind can play a key role in helping Atlantic states achieve a low carbon future grid. We simulated 2 different grid scenarios through the year 2050 using the NREL REEDS capacity expansion model. And the graphs at the bottom of the slide show the fraction of generation in 2050 technologies, with the offshore wind in dark blue at the bottom. So on the left, we have a more business as usual scenario, and on the right, we have a low carbon scenario. And in the low carbon scenario, we can see 85 gigawatts of offshore wind deployment in the Atlantic can represent 20 to 40% or even more of generation in the Atlantic states of PJM, New York ISO, and ISO New England. To study these offshore wind topologies, we translated the 2050 capacity build out from the low carbon scenario into more detailed transmission models so we could understand how these network topologies could potentially work in more detail. And the low carbon scenario considers a 2050 future with 95% carbon emissions reductions from 2005 levels and a significant electrification of additional end use demands, primarily from building, heating, and transportation. Next slide, please. So to understand some of the challenges associated with offshore wind development and transmission development in a crowded sea space with different uses of the ocean, different conservation goals, we collected 26 different layers that represent some of these potential challenges to developing that offshore wind transmission, the offshore wind and the transmission associated with it. And these include conservation, shipping, military, seabed properties, and other categories of data layers. And we considered a similar list of layers for siting offshore wind generation. And then we assigned varying levels of friction or exclusion to different locations based on these siting challenges. And we created hypothetical cable routes based on an automated or programmatic method that avoids the exclusion and the higher levels of friction wherever possible. And these layers and the friction values that are applied were based on discussion with the stakeholders and experts through our technical review committee process. So the map on the right shows a geographic depiction of the resulting friction and exclusions for transmission specifically, based on these layers for the whole domain. The black areas are exclusions, and the varying shades of orangish reddish show the varying levels of friction in all the areas of the domain, with the darker colors representing more friction. And we created our path routes, basically connecting every feasible generation location with every pre-identified point of interconnection. And then that superset of routes is used for comparisons in the topology design stage, which Luke will talk a little more about. This process is not a substitute for a siting study or a permitting process, but it can help us identify key challenges and possible major barriers for offshore transmission deployment. Next slide, please. Great, so I am going to pass it to Luke now to show some of these diagrams and maps that I mentioned earlier. First, just wanted to remind about 2 key caveats for interpreting these. As I mentioned already, the points of interconnection and the associated cables, they're not intended as prescriptions, but as creating a plausible set of connections so that we can make comparisons between the topologies. And second, this is not a siting study or a permitting study. So please keep those in mind as you're looking at the maps especially. So now I'll pass it to Luke, who did a lot of the heavy lifting for the study with the data, the production cost modeling, and the resource adequacy modeling.
Great, thanks Greg for that. And with Greg's caveats in mind, we'll go to the next slide. And we do want to say, the NREL team, as well as the DOE and PNNL teams, did do a fair amount of analytical work here on the unique opportunity that these 85 gigawatts provide to add offshore wind, to add transmission capacity to the US Eastern Interconnect and to the Atlantic states. So, and we did do some amount of work on balancing 3 main elements in the design of that radial topology and which points of interconnection would be used on the existing Eastern Interconnect grid. So the 3 main things that were balanced are the per megawatt hour cost of wind based on the wind resource depth and other factors, the electrical favorability of potential points of interconnection with some input from stakeholders on which POIs they thought were more and less feasible, as well as other studies conducted during the time that we've been doing our study. And then also some consideration in our analytical tool of the cable distance that would have to be built between where the offshore wind platform is and the point of interconnection, with consideration of those path routes for the ocean co-uses that Greg was mentioning earlier. Existing lease areas are assumed to be developed. And then the other thing to note here is that the radial topology, as Greg said earlier, is used as the basis for other topologies. So these cables that you see sort of sketched out on this map on the right side of your screen will exist in all other scenarios and topologies that we're about to talk about. And they sort of form the basis for delivering offshore wind generation to points of interconnection onshore. The platforms, we should say, do have the potential to be interlinked with direct current or alternating current technologies. You know, a big part of the potential benefit here is that there may be different or lower permitting challenges to building some of the interlinks that we're about to talk about compared to doing onshore expansion. And then the final thing that we kind of considered here in developing the topologies before we talk about them is, you know, when we ran those scenarios originally in 2050, with the generation build out from our Reeds model, we're able to observe price differences between some of the different points of interconnection. And that helps, you know, if there's a really big price difference, there's potentially a lot of value there in building a transmission line. And that also helps kind of inform some of the lines that were built. But again, not a comprehensive siting analysis. So with that said, we'll go to the next slide to discuss some of the specific topologies. So the first one is this interregional topology. So the interregional topology is shown here on the middle slide, and then sort of in that subway style map on the slide that should be on the right, or on the figure that should be on the right side of your screen. The interregional topology, it is comprised of 7 new cables that are each 2 gigawatts and interlink 11 offshore platforms to form a total of 14 gigawatts of new interregional transmission capacity that can then be used both in real life, potentially if built, and in our Plexos model to achieve a lower cost operations for the grid on an hour-by-hour basis. We should say that each network uses or is assumed to use multi-terminal high voltage direct current technology with the 525 kilovolt bipole design. And again, 2 gigawatts is the sort of rated capacity of each of those 7 lines. The choice of that technology is based on what is currently being designed, procured, and built in Europe, and could sort of form the basis of a standard design that could be used in North American projects too. I think the main thing to note here is, you know, this enables additional interregional transmission capacity that can have value to the states up and down the Atlantic coast by reducing the cost of serving future electricity demand. So with that, we'll go to the next slide. So another philosophy that might be worth pursuing is sort of what's formulated in our intra-regional transmission scenario. So in this situation, instead of those 7 cables going between regions like PJM and New York ISO, Greg, did you want to jump in with something?
No, I'm having next problems.
Instead of those cables going between the different system operators on the East Coast, they would instead stay within, you know, say ISO New England or New York ISO, which might alleviate certain barriers and in general could be additive to the inter-regional benefits. We'll get sort of to the benefits in the subsequent slides with Amy. You know, this is not going to take advantage of quite as much price diversity between the different system operators that already have a number of transmission constraints that sort of set limits on how much power can be flowed, say between, you know, Maryland and New York or New York and Massachusetts. But it does take advantage of shorter offshore interlinking cables and therefore could be a lower cost approach and potentially with lower barriers around sort of regulatory and interregional issues that I'm sure lots of folks on the call know more about than I do. So with this intra-regional topology, we do also have the option of sort of, we consider our intra scenario that combines this topology with the one that you saw on the previous slide and sort of lets us say how additive those are from a dispatch and value and resource adequacy perspective. And that is kind of the fourth scenario that we consider, or the third. So intra, inter, and then we have one that combines intra, inter. So those are the three that we build on top of the radial. And then one final scenario we consider will be on the next slide. So the final scenario we consider is the backbone scenario. The philosophy here is about sort of adding an additional set of cables that span the entire geographic area of the study. So run from South Carolina with sort of some different places that it would connect to platforms along the way, and then all the way up to southeastern Maine. So you kind of see that in that pink line that runs throughout the middle depiction on what you should be seeing. And so this set of backbone cables adds an additional 8 gigawatts of capacity in 4 2-gigawatt intervals between the different ISOs, right? So one from CERC to PJM, then on up to New York ISO, and then up to ISO New England. And so that adds a lot of north-south transfer capacity. So you can sort of imagine that theoretically, if there's a lot of value in the complementarity between load profiles in South Carolina and those that are observed in ISO New England, and the wind is not blowing at quite the same times, and so that frees up that transmission, that backbone would then potentially provide value. Of course, it comes at the cost of building a longer line, and so got to get into the modeling details to consider what the potential trade-offs are there. So with that sums up our 4 different scenarios that we build on top of the radial. And the next thing, of course, is to have modeled them in more detail and to report some findings on what we're learning about the value of these different topologies. So with that, I'll go to the next slide. So the key findings, right? So mostly what I've described is Greg described the scenarios. I've described the design of the 4 different topologies that we've considered in detail. And next, we'll talk about the results of detailed analysis, including production cost, resource adequacy, and then Amy will focus on the economic analysis. So with that, we will move to the first set of results. Great. So the first thing that we want to highlight here is what we're seeing as the benefits of these different topologies. So this is not considering the costs yet. It's just focused on the benefit that is provided in reducing production costs, so sort of operating the grid on an hour-by-hour basis, and then also resource adequacy, which we'll talk a little bit more about later, but is generally just the philosophy around, or the ability of generation in one location to serve peak demand in another location by making use of these new transmission lines, and therefore reduce the need to build additional generation capacity in the latter region. So what we're seeing here is on the order in our results of 1 to 4 billion in annual benefit from those different considered benefits. And that makes up, the Eastern Interconnect is very big and a lot of it's not super near the Atlantic, but that makes up around 1% of the production costs that we tend to see in these scenarios in 2050. Of course, it's less when it's only 1 billion and more when it's 4 billion, but that's kind of the order of magnitude there to sort of help anchor folks. And the big set of benefits that we tend to see are from reduced fuel burn from resources like hydrogen-fired combustion turbines that are more expensive on the margin. And so the fact that regions would need to dispatch those less or need to build a little bit less of them in the first place because of the additional ability to interchange power between regions during winter or summer peaking scenarios in particular is kind of what's driving the benefit there. And then of course, there's also reduced curtailment of the offshore wind itself, right? You can imagine that if there's not ability to inject more power into New York, but there is in PJM, that then some of that wind that's blowing in New York could potentially run down into PJM and reduces some of the curtailment that would otherwise happen. So another way of looking at these benefits we'll discuss on the next slide. That is kind of what utilization we see of those offshore interlinks. So this is focused here on the interregional topology. So again, there's 14 gigawatts. 6 of them flow between NYISO and ISO New England, 6 between PJM and NYISO, and then just the 1 2 gigawatt line between the Southeast and PJM. And the thing we want to highlight here is that we see that these interlinks in the interregional scenario flow in both directions in every season. So sometimes they run south-north, sometimes they run north-south in order to reduce production costs. And the utilization is kind of on the order of 50 to 60%, right? We wouldn't expect it to be 100% because sometimes the wind is blowing and the POI can only accept so much generation. So you can't just sort of route more around and then send it to the POI if the offshore wind that's connected to that POI is already maxed out. But we do see pretty high utilization, and that is sort of driving value that flows in both directions between the different interlinked regions. And with that, I'll go to the next slide. Great. So I think I kind of mentioned or previewed this earlier, but a lot of the value that we see is from the ability, the increased ability of offshore wind to contribute to peak demand situations, either natively or by using, especially by using the interlinked transmission. So folks are probably somewhat familiar with the idea that in a lot of these future scenarios that we model in REEDS and some of our other tools, there tends to be a shift towards a winter peaking system as we do things like electrify heating demand by using heat pumps. And offshore wind tends to have higher capacity factors in the winter than in the summer. And so for colder regions in particular, like New York and New England, if they're serving their heating demand with electrification of end uses, then the offshore wind complementarity with that peak demand tends to increase. And the other thing that can come from that is that as you link regions like New York or New England with regions like the Southeast, where currently those regions are sort of more summer peaking, and because winter is not quite as harsh in those places as it is in the Northeast, you get the potential for situations where the Northeast is peaking more than the Southeast is, and you can send additional power using those interlinked topologies up to the Northeast to sort of create value and reduce the need to run hydrogen fired turbines or other higher cost resources. So that kind of increases the value compared to maybe what folks would think of today. So with that, I'll do one more slide on the next one about kind of the resource adequacy piece. So, like I just mentioned, there's this question of not only backing down existing resources, but how many resources, generation resources, do you need to build in the first place to make it so that you can serve expected peak demand, with some tolerance for the fact that we don't have perfect foresight of the future. And so demand might be a little higher than you expect in certain hours. And this kind of generally speaking goes under the header of resource adequacy, right? So resource adequacy kind of focuses on the ability of the build of generation capacity to serve expected peak demand with some risk tolerance. And traditionally, resource adequacy tends to consider the contribution of generation resources, but we were able, using NREL's probabilistic resource adequacy suite, which is a sequential Monte Carlo tool that has the ability to represent different zones and transmission, we were able to consider the additional value that offshore wind has in reducing expected unserved, the interlinked transmission has to use the offshore wind or pull, even resources, say in the Southeast that can flow on those lines and up to the Northeast, to reduce the necessary generation capacity build in different regions and therefore contribute to resource adequacy. So generally, I think what we're seeing here is that the interregional builds, including the backbone, tend to contribute more because they take advantage of more complementarity between regions. And we tend to see, on the order of 25 to 40% of the nameplate capacity of the offshore wind transmission that is built can sort of contribute to reducing the needs to build equivalent firm generation. You can think of this as like combustion turbines that otherwise would have to be in those areas to achieve the desired level of adequacy. So with that said, that's another big benefit that goes onto our stack. And then we can kind of compare benefits against costs and do some economic analysis. And to discuss that, I'll hand it over to my colleague, Amy Rose.
All right, thanks, Luke. We can go on to the next slide. So this slide compares the benefits in terms of cost savings of our different topologies to the additional costs of building and operating those topologies on top of a radial topology. And what we see is that the benefits outweigh the cost by a ratio of more than 2-to-1 for all of our topology options. The table on the right shows the annual net benefits. So that's the total savings minus the annualized transmission cost. And then on the far right, the benefit to cost ratio. The topologies that have interregional interlinks, so that's our interregional, intra, and backbone topologies, have the highest net benefit and benefit to cost ratio. And although the intra-regional philosophy in this first row has the lowest net value and benefit to cost ratio, the benefits still outweigh the cost by more than 2-to-1, so it's still substantial. And then another thing to note is the interregional and intra-regional benefits, so these top two rows, are mostly but not fully additive, showing that these two strategies are complementary and could be mixed, and pursuing one might not necessarily saturate the economic opportunities for the other. And then finally, although the additional cable in the backbone topology is very long and estimated to be potentially very expensive, the benefit to cost ratio is only a little bit smaller than pursuing simply the interregional topology. And the net value in terms of dollars saved every year is significantly higher than a lot of these other topologies. We can go on to the next slide. So after seeing the benefit to cost ratios of larger than 2 for all of our topologies, we wanted to design some analysis to understand how robust these conclusions were to different assumptions. So we focused on the interregional topology only and designed a set of sensitivities varying different key assumptions that the study team and our stakeholders felt were important or interesting or could have an impact on the results. So the chart on the right shows the cost benefit ratio graph for our different sensitivities as well as our core interregional scenario in black. But important to note that this is only showing benefits in terms of production cost savings. We did not run all of the sensitivities through our resource adequacy tool, PRAS, that Luke talked about. But even without considering any potential benefits from a resource adequacy point of view, all of the benefit to cost ratios for these sensitivities are above 1.2. So we'll start on the left and kind of move left to right. As I mentioned on the far left, this is our core interregional results for that topology. And next, we tested a sensitivity called onshore extension, which hypothesizes what if we had additional transmission onshore east-west across PJM to alleviate some congestion that existed in the model due to high renewable builds in the western part of PJM. And what we found is that this congestion relief leads to more lower cost generation that can be transferred to high price areas along the interregional network on the Atlantic coast. And it leads to significantly higher production cost savings than if we were just to build the interregional offshore topology alone. The next two sensitivities, the cable limit and the limit radial sensitivities, involve limiting the flows along the offshore cables in various ways. So the cable limit sensitivity considers what if the interlinking cables could only carry 1.2 gigawatts compared to our original assumption of 2 gigawatts. And we see that that does reduce the benefit to cost ratio of that offshore topology. The limit radial sensitivity considers What if there are limits on the export cables that only allow one-way power flows from offshore to onshore, and it doesn't allow exchanges of power from one point of interconnection, or POI, to another via the offshore network? This change had the largest negative impact on the benefits of the offshore network and reduced the value by 40%. Because we found that a lot of the value of the network comes not just from being able to send offshore wind generation onshore, but during times of low wind output, when the network is being used to facilitate more power flows among regions. And then finally, the next 4 sensitivities are changes to the price of hydrogen and how that might evolve by 2050, as well as the cost of the offshore network. And these had a noticeable impact, positive or negative, to the benefit to cost ratio, but they didn't change the overall conclusions of the study that this topology was highly valuable. We can go to the next slide. And so while the system-wide value of each transmission planning topology could be high, the value to each transmission planning region in the Eastern Interconnection varies quite a bit. And similar to the system-wide savings, the regional value of transmission is highly sensitive to what we assume about onshore transmission expansion, how the offshore network would be operated, as well as technology prices and costs. The figure on the right shows the range of total adjusted production cost savings across all of our interregional sensitivities. So those are the sensitivities I just talked about on the last slide. But now we're looking by region on the x-axis. And the adjusted production cost metric, that's the difference in total production cost for each region, adjusted for import costs and export revenues to take into account trade that's happening between the regions. So what you can see is that among the different planning regions, the value of the offshore transmission network accrues almost exclusively in PJM, in New York ISO, and in ISO New England, where most of the offshore wind POIs are located. Regions that can displace high-cost generation with low-cost offshore wind or imports from other regions, such as PJM, see the largest savings across all of our sensitivities, and as well as the different topologies. And while PJM has the highest savings in terms of absolute dollars, as a share of total regional cost, it's actually New York ISO and ISO New England that see the largest savings. In this interregional topology, their system savings fall by about 4% compared to our radial case. In even more integrated topologies like the backbone, they're seeing system savings of around 7%. Other regions are benefiting by greater use of their most efficient or lower cost units for local consumption, or being able to export more to neighboring regions using the interregional network. And by contrast, if we look at regions like MISO, SPP, regions in the Southeast, they have fewer opportunities for cost reductions because in 2050, they see lower use of high cost generators that could be displaced by imports or offshore wind. And they also have fewer points of interconnection to facilitate power trade with other regions. Across all of our sensitivities, the highest transmission value occurs in scenarios that have high hydrogen prices, because the network transmission allows regions to exchange power and reduce the use of high cost generation like hydrogen. They were also highly sensitive to the level of interconnectedness. So thinking about like the onshore extension sensitivity, as well as constraints about how power might flow across the offshore network. Next slide. Now, outside of these core topologies, we did design another sensitivity to address whether there could be some low-hanging fruit opportunities to connect nearby platforms that might not be suitable as part of kind of a larger network build-out, but might make for single interlink networks. These opportunities could be much lower cost, but still have substantial benefits. Now, we didn't do a full path routing and cost analysis on this sensitivity, but we did identify 5 short interregional interlinks offshore and perform a benefit analysis on those. And what we found is that these 5 short interlinks could achieve about 2/3 of the benefits of our interregional network. but they might have significantly less than 2/3 of the cost because these are much shorter distances and fewer cables that would need to be built. So the map on the right shows a few of the general areas where these opportunities might exist. It does not show specific developed interlinks. And it focused on areas that have good wind resource and relative proximity to multiple regions. Now, these opportunities might be limited, and some of them may be in existing lease areas. So this is definitely an area for future work to potentially identify, are there some of these low-hanging fruit opportunities for interlinking? Next slide. And then, as Greg alluded to, we focused the bulk of our analysis on the year 2050, when offshore wind deployment could be significant and the transmission network is assumed to be developed. But we also wanted to hypothesize a feasible pathway to build out that offshore network from 2030 to 2050. So these subway-style maps show a potential way the interregional topology could be developed as an example. We assume that multi-terminal HVDC technologies would not be available for development in wind areas being developed in 2030, but they would be available by 2035. And several of the platforms in the interregional network could potentially be developed in 2035 based on economics and policy and the needs of the grid. But in order for these specific platforms to participate in a larger interregional network down the line, the transmission would either need to be pre-planned or developed in phases with technology standards that allow for future interlinking. Now, some of our project stakeholders have noted that a phased development reduces risk compared to pre-planned transmission. But in order to phase the transmission and also take advantage of the potential benefits of an interregional network in the future, technology standards would need to be developed very soon because projects in service in 2035 will likely be procured in the next couple of years. So in this example, if these 4 initial platforms that you see in the 2035 map are installed without standards that would allow for interoperability with a multi-terminal network, then they wouldn't be able to participate in an interregional network down the line, potentially removing a major portion of the value of that topology. Next slide. And then finally, we mentioned earlier that we'd be focusing most of the content in this webinar on analysis we're able to economically quantify. But I did want to mention some of the reliability explorations we did, focused on identifying gaps and analysis capabilities and studies that may be needed as part of the offshore transmission planning process. This was not a comprehensive reliability analysis, but the teams did develop some new tools and extend some existing tools to demonstrate the offshore wind transmission use case. So the first example here is using NREL's ASSET, or Automated System-Wide Strength Evaluation tool, to do some screening of the different POIs to determine which POIs might be weak and in need of more in-depth study and possibly additional equipment to ensure stable and reliable operation. So you can see some of the ones that might potentially be weak in these red dots on the map on the right. We also have some ongoing work on multi-terminal HVDC protection to help understand what capabilities are necessary to protect the system. Shahil Shah of NREL is the best point of contact for questions and to learn more about some of these tools and methods. Next slide. And then our colleagues at PNNL also did some really interesting reliability work using the Offshore Wind Integration Tool, or OSWIT, in combination with their chronological AC Power Flow Automated Generation Tool, or CPAGE, to prepare power flow cases, providing a really useful demonstration on how the data from our large nodal production cost models could be converted for power flow analysis. They also used the Electrical Grid Resilience and Assessment System, EGRAS, to demonstrate the concept of grid resilience modeling in a hurricane use case. And then finally, PNNL demonstrated how a multi-terminal HVDC redispatch method could help understand how the multi-terminal network could possibly help mitigate on or offshore contingencies. So if you want to learn more about any of this, Bharat Vyakranam of PNNL would be the best point of contact for questions on these tools. Next slide. And then just to wrap up, so this study helped demonstrates the potential value of interlinking offshore networks, especially interregional networks. But the landscape for offshore wind and offshore transmission is continuing to evolve. So we also identified a number of areas where continued analysis and further study would be important to determine more details of what types of networks might make the best investments. And in addition to this study, I also wanted to note the Department of Energy is funding several other relevant projects. If you're not already following, you might want to check out, including the National Transmission Planning Study and several projects on HVDC technologies and standards. Next slide. And finally, thank you very much. I have included our contact information as well as that of Shahil and Bharat if you want to learn more about their reliability work here. We're happy to take questions.
Thank you so much, Amy and Luke and Greg. That was excellent. We have a lot of questions on Slido, and I wanted to try and maybe package some of these high-level topology questions together. So there are some questions asking, does building offshore transmission across regions help in unlocking existing transmission bottlenecks? And things like, have you thought about removing some points of interconnection and instead just using the offshore network? And how did you think about, how did you design these topologies? Why didn't you use an optimization-based framework instead? These are sort of all around the topology question.
Yeah, I can take a cut at that, Amy and Luke, if that works for you. Yeah, I'll take a cut at the first one first. That was the question about whether it would these topologies could help unlock existing bottlenecks, and I think help is a useful term here. It's not going to be a single magic silver bullet solution, but it can definitely help flow power during times of need. I think Luke mentioned that you know, when the offshore wind is blowing, that's the time that you can use some of these networks the least, these offshore networks, because your export cables are already filled up. Whereas when you don't have a lot of offshore wind, you can potentially use the network to flow power north and south, and those might be the most important times. And I think that's why our resource adequacy tool was seeing a lot of potential value towards the interlinking. So I think it can help. But I don't think it can replace, you know, all transmission expansion. And I think that the I'm gonna mess up the acronym, but the NEETC transmission corridors of national interest, all out of order, you know, shows some value potentially between New York and New England, and between New York and PJM, that would also be corridors that could help, that this could help with. So so yeah, I think it can be helpful, but it's not a replacement to transmission planning the way we do it today.
Okay, great.
And I forgot the second question already.
Oh, yeah,
Back to that.
So about removing some of the points of interconnection and replacing that with just the offshore network.
Yeah, so what the technology we studied for the HVDC interlinks was multi-terminal HVDC 525 kV bipole design that would take 2 gigawatts per cable bundle. And so you still have to land those 2 gigawatts, you still have to land that cable bundle somewhere, whether you minimize the landfalls and go to a wide range of points of interconnection, or whether you minimize the points of interconnection. If you minimize the points of interconnection, you might need to do additional AC expansion at those points of interconnection. So there's definitely some trade-offs. Most of our points of interconnection, I think this is correct, most of them were single cable landings, but there was a relatively small number of very favorable points, like on the PJM 500 kV network, for example, that would take, that could potentially take 2 or more injections. I think
Yes.
you bundled together another question there, I thought, but that I wanted.
Oh, yeah, I bundled in another question around why didn't you use an optimization framework instead of the limited number of topologies? Why didn't you just like let reads optimize?
Yeah, so we wanted to really kind of be able to use the sort of most detailed, most granular transmission tools to be able to assess a range of these different topologies, because you do have to make some simplifying assumptions when you're using a capacity expansion or optimization tool. And these are very unique transmission assets in that they are converter stations in the water, for example, that are being connected, and then but they're also flowing the wind towards the points of interconnection, and so that interregional transmission can only be used space on those export cables. So they are a little bit kind of different and unique. I would also point to some work that Jim McCallie and Iowa State is doing as part of a wider team for a project that's trying to do a little better job with the optimization and sharpen their tools for this specific question. So I'd point to that.
Okay.
Anything I should add, Luke or Amy?
So there's a couple questions around sort of what's happening onshore. So one is around, to what degree you factor in the AC reinforcements on the onshore side. And then another is whether you compared onshore to offshore and looked at doing more onshore.
Yeah, so for the comparison, we were primarily focused in the study on the offshore space because of the challenges that have been involved in onshore projects and the costs also. So we were primarily focused on that, and we don't have a direct sort of onshore comparison. I would probably point to the National Transmission Planning Study, which is in its final stages right now, and looks at a more traditional onshore build, and that might provide another counterpoint. And I think you asked about AC reinforcements. Yes, we did look at those. We did a relatively simplistic treatment, like an an N-0 type of build out of the AC reinforcements. They were the exact same in all of the different topologies. So we didn't do really a rigorous study as to whether, exactly what's necessary to support the 85 gigawatts, or whether there might be some savings from the interregional networks in terms of the AC build onshore.
Sure. Okay. And then there's some questions kind of taking this into a different tack, looking at, given what's happened in the offshore wind market and with, developers pulling out of projects, do you think this kind of project will be feasible?
Yeah, so a lot of our analysis has been really focused on the longer term, the lower carbon scenarios, how much value this transmission can potentially provide in that long term. So, near term bumps in the road and things like that maybe don't necessarily change any of our big picture conclusions. In terms of near term delays, there will still potentially be opportunity to implement standards and things like that Amy was mentioning prior to development of beyond the first 30 gigawatts or so. We did assume that the first 30 gigawatts in all of the scenarios would be connected radially. And so, these near-term slowdowns and cancellations and things won't necessarily affect that. But this potential opportunity definitely leverages the development of offshore wind. So at where offshore wind goes, this opportunity goes. So the opportunity comes with the wind deployment for sure.
Mm-hmm.
I would just point to thinking about some of these kind of near-term and medium-term barriers, not just the standards, but some of the other ones. DOE did publish a report, an action plan for offshore wind transmission development, and that would be a great resource to learn more about some of these other, like how are we going to create the enabling environment to actually make this happen, and what could be done.
Sure. Yeah, that's useful. I think we have time maybe for one more question. Martha Cristino asks if there's been any analysis on impacts of changing hurricane activity. So I think the idea here is that as climate change goes on and maybe patterns of weather change, have you looked at that?
Directly for this study, we the hurricane analysis we did was what Amy showed, which was more of a proof of concept. But we have a variety of under the DOE umbrella, there's a variety of projects going on asking this question. It's a really hard question. It's an extreme events question. It's a how does the resource change overall question. It's a how do demand patterns change question. It's just got a lot of parts. So I wouldn't say we have a analysis answer from this study, but it's definitely something we're interested in.
Right, and I'll just point out that NREL is making the climate change weather simulations looking forward. So there's certainly new data sets to be used.
We're trying. It's hard.
So I'm realizing it's the top of the hour and we're going to need to wrap it up. I want to thank our speakers for their hard work on the study, the presentation today. Also thank DOE for funding this, thank PNNL for their contributions to the study. As I mentioned earlier, an email is going to go out once the video file's been posted. We'll answer the questions we didn't get to. We really appreciate everyone's engagement today. We look forward to seeing you again soon, perhaps at the Forecasting and Markets Workshop that starts on Tuesday in Salt Lake City, or the next webinar by Adrian Simonson from NOAA and David Stubbe of Camus Energy on utility applications of weather forecast data from NOAA's open data dissemination. Further information on all the webinars and meetings can be found at esig.energy. You're all invited to attend. Amy, Greg, Luke, thank you once again for this really timely, really informative webinar, and thanks to all the participants for their interest. And we look forward to seeing you again in the near future.